Okay, so it's already 6:05, so I think we can start. So, yeah, so welcome to the second live session of our course. The uh, title of the course is Physics through Computational Thinking, and the instructor is Professor Aditya Sharma from ISA Global. So, and here are some general instructions of the course that we are running. So, let us begin our second tutorial. So, in the tutorial, so first I will week 2. So in this tutorial, I will talk about uh, technical prelims that has been taught in this week. So basically, I will talk about for loop and when it is convenient to use table and when it is convenient to use for. So that I will first talk about, and after that we will solve some general physics problem from undergraduate level, and we will learn how to non-dimensionalize them. So non-dimensionalize, and in this regard I will talk about some problems on, I will discuss problems on projectile motion. Hello, can you hear me?
Yeah, yes, I can.
Yeah. Okay, so in this tutorial, the second week, first I will talk about this technical thing that we have learned in this week. So use of for loop, and when it is convenient to use for loop or when it is convenient to use table, and after that I will talk about some general problem. So I will talk about a problem on projectile motion, and how to non-dimensionalize the equation that you are getting. So when we are dealing with this uh, calculation, this numerical simulations, so it is always handy to get rid of the parameter values. So one way of them is to non-dimensionalize the equation. So that I will talk about, and after that, so I will talk about a simple problem on simple harmonic motion. So why simple harmonic motion is so important in physics, and uh, so why they are so useful, that I will talk about. Okay, so let us proceed with the first thing, the technical thing that we have learned in this week. So when we are dealing with any series expansion, so suppose we have our series exponential of x, so we can write them as 1 plus x square by 2 factorial plus x cube by 3 factorial, and so on. So in general, we can write this as summation over x to the power n by n factorial, and the limit of n is from 0 to infinity. Okay, so this exponential series, we can write this as the summation over this. So first, let us plot. Let us evaluate the exponential function. So let us go to our mathematical. So we have our exponential function, and for so what will be the exponential of 5? So exponential of 5 will be 1 plus 5 by 1 factorial plus 5 square by 2 factorial and 5 cube by n factorial, in this way. So we want to suppose generate the terms that the exponential have. So what we will do? So first, so in this x we will store our values. So we will write for, so suppose we want to generate first 100 terms. So in the for loop, so we have to write this in the initial value and the final value, and so up to which we the n will take its value. So in this case, n will run from 0, and we have to now specify how we want to increment our n. So if we write this n plus plus, so n will take first 0 value, and after that it will increment increase by 1. So 0 1 2 3, in this way n will increase, and so then we have to update our x values. So x to the power n, that will be x n minus 1, the previous value. If we want to sum the values, then we have to write, so 5 to the power n. So we are calculating exponential of 5 to the power n divided by n factorial. So if we evaluate this, we will get our value of this 5 factorial, and if we want to show see the values, then we have to uh, plot we have to get the table. So table of x to the power n, and the limit of n is from 0 to 100. Okay, so we have to start here from values 1 because the initial value is x0. So if we evaluate this, someone's joining. So I think there is some issue here. My infected. Or we can do this with the help of table also. So let us do that. So table, so 5 to the power n divided by n factorial, and the limit of n let us take from 0 to 100. Yeah. So this is the element in the exponential in the expression of exponential of 5. So if we want to see this rational number, so these are the values that we will get. Now, so in this way, we can use the table function to generate exponential of 5 or any exponential. Now, if we want to see how much time it is taking, so we have to write this timing command. So it is taking this much time, and if 0.00075, and if we want to see the summation of these values, so we have to write here total. So now it is taking this amount of time, and the exponential function summation, and the exponential 5, it will give us this value. So this exponential of 5, so we can write this as 1 plus 5 plus 5 square by 2 factorial plus 5 cube by 3 factorial. So if we continue this in this way, so the value we will get that we have right now if evaluated from this mathematical calculation. So we can do this with the so now if we do this with the help of for loop, so it will take a larger amount of time. So what is so when should we use the for loop? So basically the for loop. So the for loop is basically for any update equation. So here we know the sequence. So any series when we have any series function, then we know all their sequence. This exponential one, and there can be other functions also. So just when we know the sequence, what all the terms will look like, then we can use the table function. But suppose we are solving any differential equation, and we have to know or we have to calculate an update equation. So let us see. Suppose we have a differential equation of this kind: dx dt equal to minus ax. So or any kind of differential equation I can write dx dt, which is function of x and t. Now if we want to solve this numerically, then we have to discretize the time. So the time will take value t1, t2, t3, and in this way. So t and the time step we can take as h. So if we take this, then we can write the update equation from this as x t plus h, which will be x of t at previous instance plus h into function of x at t and t. So or so suppose this is only function of x, so that will be there. So in this case, the value of x at time t plus h, that depends on the value of x at time t. So this is Euler method of uh, solving these differential equations. So there are other kind of method also, like RK2, RK4, RK3. This all methods are there. Euler backward method also. So we will talk about them later. So, so the idea is that when you are solving any kind of differential equation or something, and there is update rule. So in that update rule, the value of the value of the our variable at a time instant, that depends on the previous memory. So in that case, we cannot use our table function. So in that case, it is necessary, or we have to have use our for loop. So so let us have let us suppose an update equation of this kind. So we have suppose a update equation x to the power n plus 1 equal to x to the power n minus so suppose any function logarithm of absolute value of x to the power n into 5 or into 5. So suppose this is our update rule with which our variable x will update its value. So if we want to see the list of the value x, all the values, then we have to have use our for loop case. So how we will solve that? So let us see. So in this case, our update equation is x to the power n minus 5 log xn. So we have to write in this way. So for loop, so n, let us start from 1, and n can take values up to suppose 100, and we have to then specify the increment. So n will increase by value 1. And what is the structure? So the structure is basically x n plus 1, which will be x n minus 5 into, so we are taking the absolute value. So we have to write absolute here, and logarithmic of x n. And we have to initialize. So let us put x0 as 0.5. So we have this update equation. So if we calculate this, then we can get the table of this xn. So if we write table n, and n is running from it's happening as a table. Function. So wait a minute. Okay, so I think there is some uh, technical issue here, but this is the general idea. So you can write your update equation here, and in this case, you will get the your all the component of this uh, variable of x. So in this way, you can solve any differential equation. So which we will learn in the next week also. So now let us talk about after this technical thing. So we will now proceed, and we will we will solve some general problem on projectile motion, and then we have to then we will non-dimensionalize them, and we can see how the equations are they are behaving. So suppose we have this kind of projectile motion. So suppose we have a module is located here at a height h, and it is throwing a ball at angle theta with horizontal with a velocity v0. So in that case, so if we want to solve this problem, then we have to consider what are the forces acting on the ball. So here is only one force acting, and if we neglect the air resistance, then the force only acting on this is the gravitational force, and that will be downward. So if we coordinate system out is like this, so this is x and this is y, then the force acting is minus mg j cap. So if we want to solve its show its free body diagram, so we have our velocity v0 and the angle is theta. So the velocity along this x-axis will be v cos theta, and velocity along y-axis will be v sin theta. And here the only force acting is on the x is on the minus j direction. So if we write the our equation m dv dt as force, then our there is no force in the x direction. So m dv dx will be 0, and m dv y dt it will be minus mg. So in this case, Vx will be constant. So Vx as a function of time, it is constant, and Vy as a function of time will be minus gt plus a constant. So Vx at t equal to 0, we know that it is V cos theta, because we are throwing the ball at an angle theta with the horizontal. So this Vx at all time will be V cos theta, and Vy at time equal to 0, we know this is V sin theta. So at time equal to 0, this term will be 0. So C has the value V sin theta. So we can write our force equation. We can write our velocity components. So Vx turns out to be V cos theta, and Vy turns out to be minus Gt plus V sin theta. So this is our velocity. Now if we want to calculate its position, then we have dx dt equal to v cos theta. So it will give us x at time t at as v cos theta into t plus constant. So let us write down this as c, and dy dt, this will be minus gt plus v sin theta. So if we solve this, we will get y of t as minus half gt square plus this will be v sin theta with a t multiplied, because we are integrating, and here will be another constant vector c prime. So what are our initial condition? So we have so to get these constants, we have to know our initial condition. So what is the value of x at time 0 and what is the value of y at time 0? So that we have to know. So from the picture, we can clearly see that at time equal to 0, when we are launching from this position, our if we take this origin to be our this 0 point to be our origin. So if we take our 0 point to be origin, then at time equal to 0, the x position is 0 and y has value h. So if we write down this, so x at t equal to 0 is 0 and this is h. So at t equal to, if we put t 0 here, so we get c 0, and if we put t 0 here, so we will get c prime as h. So our equation of this position along x axis will be v cos theta into t, and along y axis it will be h plus v sin theta into t minus half gt square. So this is our x and y position as a function of time. Now suppose in the problem we want to know how far, like this displacement. So suppose this is x0. So up to how far this ball will hit this inclined plane. So to know that, we have to know the trajectory of the ball. So trajectory means we have to find the relation between x and y. So we have x as a function of time and y as a function of time. So from there we have to find out x as a function of y. So this will give us our trajectory of the ball. And if we want to know where the ball is hitting this inclined plane, then we have to know the equation of this inclined plane also. So the trajectory of this inclined plane, how they are describing in x and y coordinate, that we have to know. So let us proceed. So this is our x and y equation. So from here, we can from the first one we can write t. So we have to eliminate t. So t is x by v cosine theta. So if we put t in this equation, then we will get the relation between x and y. So and that will be, so we have y to be h plus v sine theta into t minus half gt square, and we have our t to be x by v cosine theta. So if we put our t in this equation, then we will get v sine theta into x by v cosine theta minus half gx square by v square cosine square theta. So if we simplify it, it will be y equal to h plus x tan theta minus half g divided by v square cosine square theta into x square. So this is our trajectory of the ball or the muzzle. So this is trajectory. Now we want to know the equation of this trajectory. So this is beta. So and this is our origin 0 0, and how the inclined plane is the equation of this line. So if suppose this has of length L, if it has length L, then if this is 0 0 point, then then what will be this point? So basically we can write from here that tan b will be, if we denote this as suppose m, so tan beta will be m by L. So m will be L tan beta. So we have our, so we have 2 points. So one is 0 0 and another one is L tan beta. So and as this is straight line, so what will be the equation of straight line? So if we know 2 points, so from that we can calculate the equation of straight line. Okay, so let us another. So we have our 2 points. One is 0 0, and another one is L tan beta. So what will be the equation of the straight line? The equation will be y minus y1 by x minus x1, and here we have to write y1 minus y2 divided by x1 minus x2. So if we put the value of these 2 points, then we will get y by x equal to minus tan beta, uh, positive. So the equation of the inclined plane is y equal to x tan beta. And what is the equation of the trajectory of the ball? So this is h plus x tan theta minus half. So let us write down. So equation is h plus x tan theta minus half g, divided by v square cosine square theta into x square. So this is the equation of this inclined plane, and this is the equation of this ball of that we are that is getting this projectile motion here. So this is theta, and this is in inclined as beta. So when this ball will touch this in inclined plane, so basically at a fixed value of x, when this y value will coincide with the height of the trajectory of the ball, then the ball will touch the inclined plane. So that means when these two equations intersect each other, in that case it will hit. So the y value will be same. So we can write x tan beta equal to h plus x tan theta minus half g by v square cosine square theta into x square. So if we put if we know the values of this theta, all the parameters. So if this theta, beta, and h, these are known to all, and v we know also, and g. So if we put all the values here, so then we can find the value of x. So where this ball will touch this uh, inclined plane. So so if we want to see if this in mathematical or any programming language, then first it is always convenient to non-dimensionalize the equation. So how equation is being non-dimensionalized? So the basic idea is that suppose you have a equation. Suppose you have a equation of x as a function of time. A, so suppose x square omega square t and all this, and there are constant also. So a, and suppose this is beta. So this constant, they have unit, and this x and t, these are our parameters, or these are variables. So when we want to non-dimensionalize the equation, so we have to find the length scale of our given problem with the given parameters. So with the help of the parameters alpha, beta, and omega, So we have to construct a length scale. So with the help of these three, we have to find suppose alpha to the power a, beta to the power b, and omega to the power c. So we have to find this a, b, c value such that this has the dimension of length. So and if so if when we will find our dimension of length, then we can replace x as this number. So suppose this is p, so p into x. So p here has the dimension of length, and this is the dimensionless number. Similarly, with the help of parameter, we have to find a constant or a form of this combination of this in such a way that it will have the dimension of time. So if so suppose this is m, then we will replace our time as m into t. So basically this x and t, so this is our just number, and if we multiply this x with that length scale, then we will get our value of x, and if we multiply this t with this time scale, then we will get our time variable in the of the original equation. So so let us solve this our given equation. So this is our first equation, y equal to x tan beta. So y equal to x tan beta. So here we have only one variable, like the variable of length. So then and the length scale that and natural length that is given in the problem is h. So we are projecting from height h. So we can write this y as h into capital Y and x as h into capital X. Note that this h has a dimension of length, so the dimension of y and h is same, and this is a dimensionless number. And similarly, this x, it is also a dimensionless number. So if we plug this here, so y we can write this as h into y, and x we can write as h into x tan beta. Then we will get y equal to x tan beta. So in this equation, here the y and x, they have dimension and they have dimension of length. But in this equation, this is just a dimensionless equation. This y and x, they are purely numbers, and if we multiply them with the h, we will get our y and x position values, which is dimension of length. And similarly, the second equation that we have is this: y equal to h plus x tan theta minus half g by x square, sorry, v square cosine square theta into x square. So here also we will replace this in this manner. So we will replace y by h into y, and this is h, and this will be h into x into tan theta minus half g by v square cosine square theta into h square x square. So from this, the equation that we will get is y equal to 1 plus x tan theta minus half g h square. This will be h, 1 h will be cancelled, and here we have v square cosine square theta into x square. So if we write this gh by 2v square, so suppose we write this as some variable, then we have our equation is y equal to 1 plus x tan theta minus beta. So suppose this is alpha, so alpha x square by cosine square theta. So this is also, so if we So from dimensional analysis, you can see that dimension of this and dimension of this has to be same. So since this is dimensionless number, then this alpha also has to be dimensionless number. You can check that this gh by v square, it has it 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 is a dimensionless number. So the equation that we get by solving the projectile motion problem. So and after that we non-dimensionalize them. So these two equations, this y equal to x tan beta and this equation, so we can plot them. So let us go ahead. So we'll basically plot both the equations. So plot. So let us first write down our equations. That will be easy. So one equation is have y equal to x tan. So we have to insert Greek letters here. So suppose this is our one equation, and the other equation we have is y equal to. So let us just write down the equations first, the dimensionless equations. 1 plus x tan theta, 1 plus x tan theta minus, suppose we are denoting the constant by gamma, gamma x square by cosine square theta. So it will be gamma multiplied with x square divided by cosine. So this is our two equation which we want to plot. So we have to write down the plot command. So plot, and where we have to specify the equations. So x tan multiplied with tan theta. So this is our first quantity, and the second term we have 1 plus x tan theta minus uh, gamma. So we have to specify. So suppose so let us just right now write down gamma. Oh, we can manipulate the value of gamma. So gamma into x square, and we have cosine of theta. So these are the two equations that we want to plot, and so and what is our variable here? So we here our variable is basically x. So let us specify the limit of x. So suppose x has value from 1 to. So since this is x is dimensionless, so we have to just specify the numbers. So x 1 to 100, and this theta and gamma value. So let us manipulate them. So we can write manipulate. So we are manipulating here two parameters. One is theta and another one is gamma. So we can write them as. So let us first manipulate theta, and suppose we will start from the value pi by 4. This is our initial value, and we will vary theta value from 0 to uh, pi by 2. So this is our first manipulate command, and we will also manipulate the value of gamma here also. So let us write down the value of gamma, and let us so so suppose initial value is zero point 0.1, and we want to manipulate it from 0.05 to 1. So we have to, I think, write down. Let us see next time. Okay. This is the length of it. Mhm. Yes, I think that pi by 2. This fine. Starting from point 1. If we specify the value of theta here, therefore this is pi by 4. Manipulate command. Plot strange. Let us see. Something is plotting here. So the value is taken as 0 is the y square. Okay, so think this I think there is some issue here. So 1 plus x 10 pi by 4 minus gamma x square by cosine theta. Gamma is 0.1. This is the limit of x. Suppose this is minus x square minus x square. Okay, so let us take a 5-minute break. So in this meantime, I will go through what is the problem, and we will continue after 5-10 minutes. Mm. Okay, so there is this issue, this pi. I have written a small. We have to write this in capital. So anyway, so this is the trajectory of the ball, and this is the our inclined plane. So uh, we can see that depending on the value of the gamma, so after for below a certain value of gamma, this ball it will pass through the inclined plane, and then we have no solution. That means the ball is not touching anywhere in the inclined plane, and it is passing here. So as we increase the value of gamma, so for a certain after a certain value, after a threshold, so this ball is intersecting on the plane, and if we keep on increasing the gamma value, then we can see that the ball is coming closer to the plane. So the range or the value of x where the ball is intersecting, so that is decreasing with increasing value of gamma. So now if we check on the value of theta, so we can see that if we keep increasing our theta, then it it will change the with which trajectory, with which angle we are throwing the ball. So so in that way, uh, we can visualize the effect of this constant, this gamma and theta, on how the uh, how it affects where the ball is touching on the inclined plane. So this is the idea of non-dimensionalization. So any equation we can non-dimensionalize by the following manner. So now let us proceed to the next topic. So this is basically simple harmonic motion. Simple harmonic oscillation or something. So why we treat simple harmonic so much in physics? So they are why they are so we give so much importance to them. So basically, suppose we have a potential, any given potential. So this is our x-axis, and this is our value of the potential. Suppose this potential has any general arbitrary kind of form, and so suppose this is our, these all points, there are local minima. What does this local minima means? That means if we have suppose a particle here, and the suppose, and this is the total, suppose this is the total energy of the particle. Now total energy means this particle cannot go here, or the or here. So if we keep a particle here, so it will be trapped in this region, and in this region this is a minima. Now if we have another particle here, so it will be trapped here. So these are local minima. Local means if we have a particle at this position, it will be it will be confined in this region, and if we have a particle here, it will be confined here. Similarly, so these are our local minima. So suppose this is a local minima point, and the value of this, suppose x0. So v depends on the value x0. So if we tailor expand our potential around the point x0, so suppose we have a function x, and we want to expand this function around a value a. So what will be the tailor expansion? So it will be f of a plus x minus a into derivative of f with respect to x, and we will evaluate this value at point x equal to a, plus half x minus a squared, and here we will have d2f dx square evaluated at x equal to a, and in this way we will go through. So x minus a cube, and we have d3f dx cube at x equal to a. So whatever the function vx is, regardless of that, we can always expand this potential around a minima point, around any point. So suppose this is our one minima, one local minima x0. So if we expand our potential around x0, we will get v of x equal to v of x0 plus x minus x0 dv dx at x equal to x0 plus half x minus x0 squared d2v dx square at x equal to x0 and so on. Now, if this x0 is a minima, local minima, then the derivative of this potential at that point, that must vanish. So it will be 0. So if this is 0, then we can write v of x as v of x0 plus half d2v dx square at x equal to x0 into x minus x0 square. Now we know that if we add any value to the potential, any constant value, so this is a constant value. So if we add any value to the potential, that will not affect our force equation. Why it is the case? Because we know that force is defined as minus dv dx. So if we add if we scale our potential like this, so v dash v plus a constant value, then dv dx and dv dash dx both will be same. So if that is the case, so adding any constant value to a potential does not change our uh, 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 the equations that we will get. So if in general, if we have this equation v of x equal to v of x0 plus suppose this del 2v del x square evaluated at x equal to x0, we can define this as a constant. So suppose this is, we are denoting this by k. So if we denote this by k, then we can write x minus x0 square. And if x0, we take our reference point, if we take x0 as a reference point, that means x0, suppose this is 0, and since adding any value to the potential does not change our force equation, so we can let this to 0. So we can assume this 0 or any constant value that will not affect our equation. So we finally have half into uh, k x square, where k is del 2v del x square evaluated at x equal to 0. So x0 we have considered to be 0. So that is why if we have any kind of arbitrary potential around any local minima, we can always express our potential as this, as half kx square. And we know that in case of simple harmonic motion, our potential is half kx square. So how it is coming? So suppose we have a spring mass system. So this is our mass, and suppose this surface is frictionless. So and uh, suppose the force acting on the mass is minus kx. So why the minus is here? Because when the block is moving in this direction, the force will act in this direction. That means it will oppose its motion. So if we expand the spring, then the force will act in the minus x direction, and if we compress the spring, so compressing mean our x is in this direction, then the force will act on this direction. So that is why the negative sign is here. That means the direction of force and the direction of displacement, they are opposite always. So if we have our force of this kind minus kx, then what will be the potential? We know that F is equal to minus dv dx. So if we integrate this equation, then we will get potential as this half kx square. This is the potential of a harmonic oscillatory motion. So what will be the solution for this? So we from Newton's second law, we can write that m d2x dt square, the force acting on this is minus kx. So we can write d2x dt square plus k by m x. Now what will be the solution of this equation? Let us consider this k by m to be omega square. So if we consider this, then we will have d2x dt square plus omega square x, so equal to 0. And what is the solution of this equation? This equation has the solution of this kind. So a cosine of omega t plus b sine of omega t. So you can check that this is the solution. So for checking, what we have to do, uh, we have to plug in the value of x and double derivative of x in the given equation, and we have to check if it is satisfying or not. So we have x to be this. So what will be dx dt? Dx dt will be omega minus a omega sine omega t, and it will be b omega cosine of omega t. And what will be the double derivative? Double derivative will be minus omega square a cosine of omega t minus b of omega square sine of omega t. So we can take this omega square common, and we what is left here? So we have here a cos omega t plus b sine omega t. Now this is our value of the x. So we can write this as minus omega square x. So from here we will get d2x dt square plus omega square x equal to 0, which is our original equation. So that means this is the solution of our equation. Now we can write this solution as other form also. So this x of t, a cosine omega t plus b sine omega t, this we can write in other forms also. So we can also write this as c e to the power I omega t plus d e to the power minus I omega t, and also we can write this as in any constant, suppose p and cosine of omega t plus phi. So any one of this will solve our given equation. So if we plug any value of this, they will satisfy this equation. Now what is the relation between this coefficient and this p and phi? So there has to be some relation. So let us find out. So this cosine of omega t plus phi, this we can write as cosine of omega t into cosine of phi minus sine of omega t sine of phi. So this p cosine omega t plus phi, this we can write as p cosine phi multiplied with cos omega t plus minus p sine omega t sine phi into sine omega t. So we want to find the relation of this a and b and p and phi. So if we compare this equation with this and this, if we compare, then we will get a will be equal to p of cosine phi and b will be equal to minus p of sine phi. So from this two equation, we can find the value of p. So if we square them and add, then we will get p squared, and here we will have sine square phi plus cosine square phi, and the value of this is 1. So p is root under a squared plus b squared. So this is the value of p, and what will be the value of phi? So from these two, we can write tan phi equal to minus b by a. So from here we will get phi equal to tan inverse minus b by a. So this is the relation between this a and b and p and phi. So if we are given e- equation like in this form, and suppose we are asked to write the displacement in this form, then we have to make the transformation here. So if we know a and b, so from there from that we can calculate the value of p and phi. And once we were done with calculating the value of p and phi, we can write our displacement in this general form. So this is the solution of our given harmonic oscillator equation. So this is if we have force in this kind, or our potential of this kind, this quadratic kind of potential, then our solution, this will have oscillatory kind of solution. So this x equal to a cosine of omega t plus phi. So this will yeah, look like this. And depending on the value a and omega, this equation, so let us manipulate them and and check. So we will plot a multiplied with cosine of omega t. So this is our solution, and plus we have our phase factor here. So phase factor is basically phi, and we are plotting this as a function of time. So let us time has value from 0, or suppose 1, from 1 to 10. And we will manipulate the value of first a. So 0.5, suppose we are manipulating for 0.5 to 5. Then we will manipulate our omega, the frequency, and suppose the initial value is 1, and we will manipulate from 1 to 10. So this is 5. And we have another uh, parameter here, the phase factor. And suppose this phase factor, so let us manipulate it from 0 to pi by 2, or pi. So this is the solution look like for this set of values. So let us check one by one what is the effect of each parameter. So what will be the case if we change a? So if we increase a, so that will only increase the amplitude. it is uh, it is not changing its shape with respect to time. So the zero position and maximum position, they are basically fixed. And if we keep on changing a, that means if we keep increasing or decreasing it depending on what we are doing, the maximum amplitude, that will get increased or decreased. Now what is the effect of omega? So if we keep on increasing omega, then then what will happen? So increasing omega means frequency will increase. So for in part time interval, the number of oscillations will increase. So if we keep increasing omega, so in this time limit, we we will see more number of oscillations. And similarly, and now what is the effect of phi? So if we change phi, then we can see that the whole spectrum or whole curve is shifting. So why it is happening? So this at t equal to 0, this x has value as a cosine of phi. So suppose we have a graph of this kind. Now if we change phi, then this value will change. That means the value of x at time t equal to 0 will change. So if we change phi, so suppose for a fixed value of phi 1, we are getting this. Now if we change phi from phi 1 to phi 2, this value of x at initial time will change. So the curve will look like something like this. So suppose it will uh, uh, look like as if the whole graph is shifting. So suppose at for a certain value of phi, we have our x value to be this, and for another value of phi we will have our x value to this. So this x value will be at time t equal to 0. So whole curve will shifted, and it will start from here. So it will look like this. So that is the effect of phase on the amplitude of this simple harmonic motion. So we have three parameters. If we keep if we increase our amplitude, the displacement, the maximum amplitude will change, zero positions will not change. And if we change our omega, then frequency, if we increase our frequency omega, then our frequency will increase. So in part time interval, number of oscillation will increase. So suppose 0 to 1, and if we have for a fixed frequency, we have suppose this 3 number of oscillation. Now if we increase omega, we will have more oscillation in part time interval. So that is the effect of omega on the amplitude. So that is why this harmonic oscillator, it is always important to study this, because as we have already seen that any kind of potential or whatever the shape of the potential is, so if we look very close to the minima for very small oscillation or for very small amplitude, so if we keep increasing in the whole range, this will not be a harmonic potential. But if we fix at a certain minima point, and we see its motion around the minima point, then whatever the uh, global nature of the potential is around that minima point, it will always behave like a simple harmonic oscillatory motion. So that is why it is always useful to, or that is why this simple harmonic oscillation study will always come back in your studies. So let us solve this simple harmonic motion. Let us solve another spring mass system. So suppose we have spring here, and one mass is connected here, and another mass is connected here. Uh, so here, unlike of the previous problem, there we have one spring and one mass, but here we have two spring connected around the position of the mass. And suppose we constant the motion of the mass around this y direction. So it is only moving in this direction, and uh, we somehow constrain the motion of this mass around this x direction. So there will be no movement around this x, and there will be movement around this y direction. So what will be the solution will look like? That means what will be the function of y, how it will look like in time. So for that, we have to solve the equation of motion. So that means am d2y dt square equal to f. So that we have to solve. So for finding if we can always easily find from the potential, because we know that force is defined as minus dvdx. So if we know our potential, from that we can easily calculate our force. And since this potential is a scalar function, so it is always it is easy to work with this potential rather than force. So we will work with potential. We will calculate what will be the value of the potential, and from there we can get the value of the force. Now suppose if the mass makes motion in this direction, then what will be the spring constant look like? So now it will look like this. suppose the displacement along this direction is y, then we know for spring what is the potential. So for one spring, if we if the if its natural length is x0, and we increase its length by an amount x, then the potential energy. So suppose this is our natural length, and we increase this. So suppose this is x. So this is in equilibrium, and we disturb the system, and we expand the spring to a length of x. Then the potential energy stored is half k x minus x naught square, where k is what? K is what? The spring constant. So similarly, uh, we have to find how much by how much amount the both the spring have expanded. So what will be the expansion? So initially, if its natural length is a0, and now what this length is, so this is a and this is y, so this will be root under a square plus y square. So this is at initial position, and this is the length after stretching. So what will be the difference? So the difference will be a squared plus y squared minus a0. So this is initial and this is final. And what will be the potential energy? Potential will be half k squared. So this is for one spring, and since both the springs are symmetric, so for v1, let us denote this by v1 for first spring. So since the both the springs are symmetrically positioned, so the second one will also have the same potential. So the total potential of the system will be 2 times v1, since v1 and v2 are same. So you can write this as k multiplied with a square plus y squared minus a0 squared. So this is our potential. So if we know our potential, then what will be our force? So force is basically minus dv dy. So it will give us minus k into 2 root under a square plus y square minus a0, and we have to differentiate this. So this will give us d dy of root under a square plus y square. Now we will treat the case for small oscillation. So what does this small oscillation means? So if this is our system, then the displacement along the y direction, it will be very small compared to the length of this a. So y will be very small compared to a. So this is our small oscillation approximation. So let us first look what will be the how the potential will look like in the small oscillation approximation. Then we will calculate the force. So the potential is k multiplied with a square plus y square minus a0 square. So for a we can take outside. So a0 squared into a by a0 squared plus y by a0 squared minus 1 square. So this is how the potential look like. And if we want to non-dimensional, so when we want to solve this in numerically, we have to first non-dimensionalize it. Now for the small approximation, this a square plus y square, this we can write as, so 1 plus y square by a square to the power half. Now, if y is very small compared to a, then we can write this as a into 1 plus y square by 2a square. and if we multiply this with a, then we will get y square by 2a. So what will be the our potential look like? So potential will be k into a minus a0 plus y square by 2a and square root of this. So this is our potential. So from this potential we can calculate the force. So potential is k into a minus a0 plus y squared by 2a square. So if we want to calculate the force, then force will be, sorry, this will be y. So dvy with, so the derivative will be with respect to y, and it will give us minus 2k a minus a0 plus y square by 2a, and we will have 2y by 2a. So basically we will get minus k by a into a minus a0 plus y square by 2a into y. Now this a term we can plug in back inside. So it will be a minus a0 by a plus y square by 2a square into y. Now if y is very small compared to a, then this y square by a square, this term we can treat this as 0, because already y is very small compared to a. So if we square the term, then it will be more less. So that is why we can treat this term as 0. And if we consider this, then our fourth equation will be minus k into a minus a0 by a into y. So this is our fourth equation. So if we plug this in our equation, then we will get m d2y dy square. It will be minus k into a minus a0 divided by a into y. So we can write this as d2y dt square plus omega square y. So this is exactly similar to the our equation of simple harmonic motion. And what is omega here? Omega is here k by m into 1 minus a0 by a. So this is our oscillation frequency. So so the solution of this will be a cosine of omega t plus phi. So how we can calculate this a and phi? This a and phi we can calculate from the initial condition. So since this the equation here we are dealing with is a second order equation, to solve a second order equation we need two constants. So if we have d2y dt square, so we need to know two constants. So that means, so suppose we know y at t equal to 0 and dy dt at t equal to 0. So if we know these two value, so from that we can calculate these two coefficients a and phi. So suppose y at t equal to 0 is 0. That means we will get, if we put t 0 here, we will get a cosine of phi equal to 0. And suppose dy dt at time t equal to 0, suppose this is v0. So then dy dt will be minus a omega. From the equation we will get this sine omega t plus phi. So at time equal to 0, this will be minus a omega into sine phi. So if this is v0, then we will get a sine phi minus omega a sine phi equal to v0. So if so from this equation either a is 0 or phi is 0, but if a is 0, then our y will always be 0, and that is a trivial case. So if we don't perturb the system, that is the solution for all time. So if we don't expand this in y direction, the spring mass system will always rest in equilibrium, and in that case the displacement along y direction will always be 0. So a equal to 0 is a trivial solution. So other thing that can happen is this cosine of phi, this is 0. So this implies that phi is pi by 2. So if we plug phi pi by 2 here, then we will get minus a omega equal to v0. So this a will be minus v0 by omega. So the equation that we are getting y is a cosine of omega t plus phi. So it turns out that this phi is pi by 2 and a is minus v by omega. So if we plug them, we will get minus v by omega into cosine of omega t plus pi by 2. But this is minus sine phi by 2. So this will give us v by omega sine of omega t. So this is the solution of our given problem for any time. And what is omega? Omega is root under k into 1 minus a by a0 by a. So this is the solution of this spring mass problem. Of this problem, if this is confined is in this direction. Now, if the spring is confined to move only along the y-axis, then if you do the calculation in same way, that means first you calculate the potential energy stored in both the spring, and from that you get the force equation, and you solve. If you solve this, then you will also get this simple harmonic kind of motion along this x direction also, and in that case the frequency is root under 2k by m. So this is along x direction and this is along y direction. So what is the so the ratio of them will be half into 1 minus a0 by a. So in that way we can solve any kind of problem of this kind. So basically first we will have to we have to find the potential, and from that we can calculate its force, and we will get its how the position will change with respect to time. So this is one kind of harmonic oscillatory motion. So let us treat another very familiar which we already encounter almost in our college or BSc days. So this is any simple pendulum. So this is a very well-known problem. So we have so suppose we have a spring. We a simple pendulum is hanging from a thread, and it is we know that it will move in this kind. Now let us solve its equation of motion, and let us see how it's look like. So suppose the angle here is theta. So to solve this equation of motion, first we need to know its free body diagram. That means what are the forces that are acting on the system, or we can also calculate from the potential also. So if we know the potential, we can know the force. So the forces that will act on this will be, one will be the gravitational force, that will be in this direction, and another, and since the ball is hanging from the thread, so it will have another force in this direction. So if we solve this in polar coordinate, then in polar coordinate will be, so this is our r cap direction, and this is our theta cap direction, and this is the direction of force. So this mg, we can write this as m into g, and if this is since this is theta, so this is also theta. So this component will be cos theta along r cap, and along this this theta axis, it will be minus sine theta cap. So this is and the tension, it will be along the negative r axis. So these two are the forces that are acting on the system. uh, Now we are interested in the motion along this phi cap direction, or along this theta cap direction. Then in polar coordinate, how does the force equation look like? So in polar coordinate, we can so suppose we have a polar coordinate, and this is the position. Then this position we can write as r and r cap. So r we can write this as r cap. So if we take its derivative, that means the velocity in position coordinate will look like r dashed r cap plus r r cap dash. This are the unit vector that will change with time. Why that so? Because if any object is moving in a circle, suppose, then at this point its r cap will be in this direction and theta cap suppose is in this direction. Now if at a later time this object is moved to that point, then its r cap will be in this direction and theta cap will be in this direction. So this r cap and theta cap, they are s- uh, changing with respect to time also. So that is why, uh, a, as in case of Cartesian coordinate, this I and j we keep them fixed along a certain axis. So that is why I cap derivative or j cap derivative, they turns out to be zero. But this r cap and derivative of theta cap, they are not zero. So how they are so if this is I cap and j cap, and this is our direction of r cap, then r cap we can write this as cosine theta I cap plus sine theta j cap, and this is the direction of theta cap, theta unit vector. So theta unit vector, and if this is theta, then this will also be theta. So theta cap, we can write this as minus sine theta I cap. So this is its projection along the x-axis, and along y-axis we can write this as cosine theta j cap. So what will be r cap, derivative of r cap? It will be minus sine theta theta cap I plus cosine theta theta cap j. So if we take theta cap common, then we can see that it will have minus sine theta I cap plus cosine theta j cap. But this is our theta cap direction. So derivative of r cap, it will be theta dot theta cap. So if we similarly calculate, then we will see that the derivative of theta dot, it will be minus theta dot into r cap. So if we use this value, and then we can calculate the form of the velocity and acceleration in polar coordinate. So the position in polar coordinate is defined as this. So velocity will look like this. So first r dash r cap and r, and derivative of this, we know this is theta dash theta cap. And what will be the acceleration look like? So if we go on in the same manner, then we will see that the acceleration equation, it will have r double dash r cap plus r dash, and r derivative is theta dash theta cap. It will, and if we go on like this, then the acceleration in polar coordinate will look like this: r double dot minus r theta dot square in the r direction, and in the theta direction it will look like r theta double dot plus 2 r dot theta dot. So this is in the r direction, and this is in the theta cap direction. And the pendulum, in case of pendulum motion, so we know that the force in the theta cap direction, that we have already calculated. So this is the force in the theta cap direction. So it will be minus mg sine theta theta cap. And what is the force in the r direction? It will be mg cosine theta minus t r cap. Now, if uh, the string, it is rigid, that means it is not changing in length. So that basically means in this direction, in r cap direction, there is no force. So if in r cap direction there is force, then the length of the spring will change. So as the length of the thread is not changing, that means the force in the r cap will be 0. So we have T equal to mg of cosine theta. So this is the tension of the spring. Now in the theta cap direction, what is the equation of motion? So we have this acceleration term r theta double dot plus 2 r dot theta dot equal to minus mg sine theta. Now we are assuming that the length is not changing. This implies that the rate of change of r will be 0. So this r dot is 0, and what we are left with, so we are, and the value of r is the length of the thread. So let us take to be L. Then we get theta dot equal to minus mg by L. So this there will be a m, and this m will cancel out. So minus g by L sine theta. So what is the solution? So the solution that we are getting, theta double dot plus g by L sine theta. So this is the equation of motion of this pendulum, of this simple pendulum. Now this doesn't look like our harmonic oscillatory equation, but we know that this sine theta, we can write this as theta. So this is basically theta minus theta cube by 3 factorial plus theta to the power 5 by 5 factorial, and so on. Now for very small value of theta, if theta is very small, then we can neglect all these higher order terms, and we can write this sine theta to be theta. We can approximately write this, and if we plug in this equation, we will get theta dot plus g by L theta. So this equation, this looks like our simple harmonic oscillatory motion. So x double dot plus omega square x. So this is exactly similar to our equation. And what will be the frequency of this pendulum motion? So the frequency will be root under g by L. So this is the frequency with which the pendulum will oscillate. So it will oscillate with a frequency, and this frequency, it doesn't depend on the mass. So that means uh, whatever the mass of the bob is, like the frequency will always be same. It only depends on the length of this pendulum, or on the length of the thread. But there are certain limitations, like we are ignoring here the radius of the ball and so on. So if if we keep increasing the radius of the ball, then the equation that we are working with, it will no longer be valid. And this is only valid whenever the radius of this ball is very small compared to the length of the string. So these are some examples of this harmonic oscillatory motion. So in simple pendulum, we observe this simple harmonic kind of motion, and in case of LC circuit also. So let us look at another example. In this LC circuit, we also observe this simple harmonic kind of motion. So how we, so let us first understand this physically. So what we have here, we have here a capacitor and an inductance. So if there is no inductance, so if there is only one capacitor, and if we charge the capacitor, so suppose here is a switch. So this is switch. So suppose we charge the capacitor and we close the switch. So if we closed it, then on this plate we have electron deficiency, and here is the electron, we have more number of electrons. So if we connect it, electrons will flow from this direction to this, and there will be a current in the circuit in this direction. But this current, how longer the current will be, the long as long as there is charge difference, the current will flow. And if the current flows, then the electrons will start flowing from this plate to this plate, and ultimately we have charge zero. Then the current flow will stop. So in that case there will be no oscillatory kind of motion. So if we look in the form of current, so with respect to time, at in initial time there will be a large amount of current, and after that it will be zero. So there will be no more current. Now if we connect a inductance here, then what will happen? In that case, we know that inductance always opposes the current. So if a current is flowing in this direction, then the inductance, it will generate a back EMF, and it will try to oppose the current. So the effective circuit will look like this. So we have a capacitor here, and if the current is flowing in this direction, then inductance will make sure to it will create a back EMF, and it will flow a current in this direction. I so we can effectively think of this like this, so plus minus. So the inductor we can think like this, and there will be current in the backward direction to oppose the increase of current. So if I is increasing, inductance try to oppose the increase of it, and similarly whenever the I is decreasing, inductance will try to support the current. That means it will increase the current flow. Now in that way, whenever the current will be zero, like when the charge on the capacitors will be zero, then then the inductor will make sure to make a flow of current in this direction. So in that case it will act like this. So it will create a back EMF in this format, so that the current flow is not stopping. So inductor will make sure that there is flow of current. So it will create a back EMF in this direction, and the current will flow this. And if we look in the same manner, so we can see that we will see that ultimately uh, this will come. So there will be a kind of oscillatory motion. So when the first the current will start to flow in this direction, so inductance will create a back EMF in this direction, and the current will stop to so if we look in the graph, so current will try to be zero, and whenever the current is zero, inductor will make a current flow in the opposite direction, and it will reach its maxima. So whenever the maxima reaches, then again inductor will oppose the current flow, and it will reach zero, and whenever it reaches zero, inductor will support the current flow. So in that way we will have a kind of oscillatory motion. Now let us see this with the help of mathematics. So suppose this is our capacitor plate, and this is our inductor, which so the current is flowing in this direction. So this is suppose positive. So this is at an intermediate time. So if current is flowing in this direction, the inductor will make sure to oppose the current. So that means inductor will back EMF will look like this. So it will be positive and negative. Now if we apply Kirchhoff law here, so if this is our loop, so the potential, so if we go from this direction to this direction, our potential will increase. And we know in case of capacitor, we can write Q equal to CB. So the V, we can write this as Q by C. And in this loop, so we are going from the positive to negative direction. That means our potential is decreasing. So in that case, we can write L, and we know the back EMF produced in the inductor is L di dt. Now we know that I equal to dq by dt. But here what is happening? The Here we can see that the charge on the both the capacitor, they are decreasing with time. That means dq is negative. So if dq is negative, then we have to write I as minus dq dt. So if we write this in if so di dt will be minus d2q dt square. So if we plug in the equation here, then we will get d2q dt square plus 1 by lc into q. So, so this exactly looks like our harmonic oscillatory motion. So we can write this as d2q plus dt plus omega square q. And what will be the frequency of this oscillation? So the frequency will be 1 by root under LC. So this is the frequency with which our current is with which our charge is oscillating, and we can write the solution of charge as a cosine of omega t plus phi, and we can evaluate the functions. For that we need to suppose provide with two initial conditions. So suppose our charge is given at initial point q0, and the current at initial time there is no current, so initial time our current is 0. So with the help of this two equation we can evaluate this coefficient a and phi, and with that we can get the exact form of q. So from q we can easily calculate I. So I is dq dt. So it will be, so q is a cosine of omega t plus phi. So I will be minus a omega sine of omega t plus. So we can see also that the current, it has also oscillatory solution. So if our q has a oscillatory solution of this kind, then the current will also have a oscillatory solution with with a certain phase gap. So there will be a phase difference between these two, and with which they are oscillating. So I has a negative sign, that means I is lagging. So this is if this is q and this is I. So both of them will have the same oscillatory solution, but there will be a phase difference between them. So and in that way we can also calculate energy also. So energy is half Li square and q square by 2c. So if we plug if we calculate the coefficient a and phi, and if we from that we can calculate I, and if we calculate the energy, then we will see that this is conserved. So total energy is conserved, and it is oscillating between this electric uh, energy and magnetic energy. So for a certain amount of time it is storing in the capacitor, and for a certain amount of time it is storing in the inductor, and that in that way uh, this energy, this is also oscillating, but the total energy, this is conserved. So these are some examples of this harmonic oscillatory motion. So okay, so that is it for today's video. Uh, so I will upload this and put the link and also that PPT file. So we will meet next week. Yeah, welcome.